Alright, we're going to do a few friction examples here. These are pretty simple mathematically, I think, a lot of them. So we're going to spend a lot of time talking about like the theory behind it. So hopefully we can get some help conceptually and a little math too. Alright, so a car's tires have a coefficient of static friction of 1 and kinetic friction of 0.6 with the road. What is the maximum acceleration the car can achieve? And what direction is the force of friction on them? So this is a really interesting question about how cars actually move. You might think the force of the engine is what causes a car to move, and that's sort of true, but sort of not true. If we actually look at a car, right, and the reason why we know that is because, like, if we have a car, here's my beautiful car drawing skills. Right, we have a car, here's our wheels. What if we lift that off the ground like in a garage, like it's getting repaired, right? It's up off the ground. You can put as much force on the engine. The engine can do as much as it can, but it can't do anything. Because it's actually the force with the ground that makes it go forward. There's a force on the tires from the ground that make it go forward. Now, the reason why that happens is that the tires are pushing against the ground, and so the ground pushes back. You remember Newton's third law? Right? So what the car's engine does is it makes the tires push against the ground, which makes the ground push on the tires. So if this car wants to go this way, right, this is the way it's going to go. So our acceleration is going to be that way, right? Then the force, the friction, it's the friction with the road that makes it over. So the force of friction is also forward. Okay? Now, let's think about why that is, because what we know about friction is it's about the opposite direction of, if it's kinetic friction, it's opposite direction, it's sliding, right? So let's look at the actual tire here. And let's imagine this tire is sliding. So this tire is rotating like this. This is kind of advanced stuff here. Rotating like this, okay? If the tire is rotating like this, then the tires on the bottom is actually going this way to some extent. So the force of friction is the opposite direction of that. Like, this is the direction that the bottom part of the tire is going. So the force of friction is going to be opposite that. And for static friction, right, the same thing happens. Like, it's like, oh, the bottom of the tire wants to go that way, wants to slide that way, so the force of friction is the other way. Okay? So that's what's happening. All right, so maximum acceleration. Right, so if I'm actually doing this, right, the maximum acceleration, the maximum force is when F net, right, we got the force of frictions that way. We've also got the Fg and Fn. And as I told you guys before, right, so we get F net horizontal, right, this is just going to be equal to the force of friction. And F net vertical is going to be equal to Fn minus Fg. And this whole thing is 0, right, because it's not moving vertically. So, right, this is just a situation where G is equal to Fn. Or I guess this is equal to mg, right? So here are the force of friction. So we want to maximize that. We know that static friction is more than kinetic friction. And you know this, right? If you're driving your car, you can drive faster when your tires aren't spinning, right? So we want to say F net, which is ma horizontal, is equal to static friction, the maximum. Right, which means the maximum of static friction can be is when it's normal force S. So that's ma horizontal, and this is mg. Yeah, you'll notice the masses cancel out. That's a pretty common thing to have happen in a friction problem, that the masses cancel out, as long as there's not a lot of a pushing force. That should happen. So we get the acceleration horizontal is 9.8 times 1, or 9.8 meters per second squared. So that is the fastest the car can accelerate. Okay. This leads to a slightly different conversation about what anti-lock brakes are. You may not know that much about them. Basically, anti-lock brakes are designed to make it so your tires don't skid on the ground. Okay, because as soon as you start skidding, when you brake, you have this coefficient of friction which is not very high, or not as high as the static friction one. Kinetic friction is not as high. So you want to keep this friction as much as you can. And so the whole point of anti-lock brakes is to keep your car tires rolling And rolling's good because then and it's static friction, like the tire is actually moving the same, is in contact with the ground, okay, and not sliding. All right. All right, here we got a 1 kilogram magnet, initial velocity of 5 meters per second, and the magnet is on its steel table. So there's like a 5 Newton force of attraction to the table, between the table and the magnet. The coefficient of kinetic friction is 0.4. How far does the magnet slide? Okay. So again, we have, let's do our little, here's our magnet, here's the table. We've got Fg and the force of magnetism, both down, Fn. And let's say the velocity, right, which is not a force, but let's say the velocity is this way. It's not really on my force diagram, but I'm putting it there for reference. And that means, right, the good thing is that the force of kinetic friction is always opposite that velocity, right? So we can do that. So my Fnet equations, Fnet horizontal is negative Fk. And the reason it's negative is because I'm going to make that velocity positive. So this is going to be my positive direction as well. And Fnet vertical is equal to Fn minus Fg minus the force of magnetism. The magnet's still not going vertically, so this is 0 is equal to Fn minus 9.8 times 0.1 minus 5, which means Fn is equal to 5.98. And since this is kinetic friction, we know that kinetic friction is always equal to normal force times mu k. And this is equal to mass times acceleration. So this is 0.1 a is equal to negative 5.98 times 0.4. And that's going to give us an acceleration of negative 23.9. Which makes sense, right? This magnet's really strong, so as soon as I throw it on the table, it's not like a slide bar, it's just going to like stick there. We want it. So now I've got acceleration. V initial is 5. V final is 0, right? Because it's going to slide to a stop. We've got three kinematics variables. V final squared equals V initial squared plus 2a and x. 0 equals 25 minus 47.8 and x. Delta x is 0.52 meters. Okay, so notice, this is one of the few times where normal force was not just equal to the force of gravity, and that was because there was another force in the vertical direction. This is the kind of thing you need to be paying attention to, whether you need to do this whole Fnet y at all. Right? Because I've told you guys I don't care if you just do normal force is equal to force of gravity. That's most of the time going to be true. But this is one situation where it's not. So we got to pay a little bit of attention to those situations. Okay, so we've got 10 kilogram block. It's got coefficient of static friction 0.7 and kinetic friction 0.4. We got two forces, 90 newtons to the right and 20 newtons to the left. I want to know what is the force of friction on the block. Now, unlike the previous two problems, I don't actually know whether this block is going to slide or not. So we talked about what we need to do to figure out if it's going to slide. So step one of figuring out whether it's going to slide or not is we still draw the force diagram, I guess I should say. We've got Fg, Fn, we've got 90 newtons this way, and we've got 20 newtons this way. And what way is the force of friction going to be? If it's static friction or kinetic friction, it's supposed to be this way. So the friction is going to be this way. Okay? Now, first step is to figure out we need to figure out whether it slides or not. So first, we're going to write this equation as if it doesn't slide. So we're going to assume no slide. Okay? Maybe I should write that on there. Assume no slide. Okay. Fnet horizontal is equal to 90 minus 20 minus the force of friction. And Fnet vertical is equal to Fn minus Fg. Now, if it's assuming no slide, that means the acceleration in both dimensions is 0. So this is mass times 0 equals 70 minus force of friction. This is mass times 0 equals normal force minus mg. Normal force equals mg. Here the force of, I really should have put this as static friction, right? We're assuming no slides. This is static friction. So in this case, the force of static friction is equal to 70. This is the static friction needed to prevent it from sliding. Well, what about this? What's the maximum force of static friction? It's normal force, mg times 0.7. You do that out at 68.6. Okay, so static in this case, Fs must be, actually I just said, such objects. Nope. Okay, so let me rephrase that. To not slide, Fs is less than or equal to Fs max. This did not happen, right? Didn't happen. So that means it did slide. So now I need to do this whole thing over again, sort of, except with kinetic friction. But it's pretty close, right? This is F net horizontal. Now it's 90 minus 20 minus kinetic friction. And the normal, this whole vertical situation is exactly the same. And we know that now it's sliding, so acceleration's unknown. And we know that kinetic friction is always normal force times UK. So I've got 10A equals 70 minus 68.6 times 0.4. That comes out to be 30.8 newtons, which means my acceleration is 3.08 newtons. So to find out if something slides, assume it doesn't slide. Assume it's no sliding at all. Figure out what the force of static friction is, and then compare that to the maximum. If it's less than the maximum, right, then you were right, it won't slide. If it's more than the maximum, then you were wrong and it will slide, and then you go to kinetic friction. All right, last one here. It requires a pushing force of 60 newtons to start a 15 kilogram block sliding on the sidewalk. What is the coefficient of static friction on the block? Okay, so we've talked about sliding versus not sliding. If it's sliding, kinetic friction. If it's not sliding, static friction. Okay, but the exception to that is starting to slide. Start sliding, right? So the starting sliding is the difference between not sliding and sliding. And in order to go from not sliding to sliding, you have to beat static friction. So starting to slide is a static friction question. Okay? Anytime you see this, start to slide, okay? Or anytime you see that start to slide, what that's telling you is that the static friction is equal to the maximum force of static friction, which is normal force times coefficient of static friction. That's what this is telling you. Okay? All right? Again, because in order to start to slide something, you have to just barely get past the force of static friction. That's the one thing it's telling you. The second thing it's telling you is that acceleration is basically 0. It's actually just more than 0 because you're barely starting to slide, but we're saying it's really, really close, like 0.00001, right? Because 60 newtons barely starts at sliding, just barely enough. So it's going to start sliding at a very, like, the acceleration is going to be really low. Okay, so we say, still, we've got a block, 60 newtons. Static friction is going to be the other way, right? Still Fg, Fn. So F net horizontal is 60 minus Fs max, right? We know it's this maximum. And right, we already know this, that Fn equals Fg, right? We know this. I'm not going to do the whole vertical situation again. I've done it like 3 times already. This, hopefully you've already gotten that part. This is true. There's no other vertical forces, so that's true. So F net, I really should not have that there. And that horizontal, right, is mass times acceleration is equal to 60 minus Fn us. Acceleration 0, so this is 0 is equal to 60 minus mg us. And this is 60 is equal to 15 times 9.8 times s. We can solve that for the coefficient of static friction to be 0.408. No units for static friction, right? Again, its coefficients generally do not have units. All right.